Welcome back. Today I'm going to be going over this specific constant question that usually appears or is similar to a Module 2 SAT math question. So I don't want to waste any more of your time, so let's get right into it. And before we dive into this question, please give it a try, right, before I proceed with the explanation. So we have a quadratic expression here, right, um, given, and they tell us A and C are positive constants. It tells us that the expression can be written in this form, where both j and k are also positive constants. So what is the greatest possible value of AC? Now, first things first, right? When I look at this problem, I just see a bunch of letters, right? There's so many constants. Um, so I would first lean towards what the question is asking in the first place, right? Which is the greatest possible value of AC. So we know that we're trying to maximize AC, right? Now, what are we given? Well, we're given this expression here, and we're also given that it can be written in this form, right? Because that's all we're given, I think the logical thing to do is just expand what they give us, right? So expand this expression here. So when you do that, right, just use FOIL. So you have jk x squared, right, plus j squared x plus k squared x plus jk. So that's what you get when you expand all of this. Now, why did I say expand? Well, because they give us that these two equations are equal to each other, right? Because they're just written differently, right? But they're the same. So what I would do next is match the coefficients together, right? Of the like terms. What do I mean by that? Well, the x squared term here has an a, right? Whereas the x squared term here has a jk. So you can set those equal to each other, right? And then you can do the same thing for the other terms, right? The x term here has a 130, whereas the x term here, there's a j squared x plus a k squared x. So what you can actually do is j squared x plus k squared x. If you factor the x out, right, this becomes j squared plus k squared. So therefore, 130 equals j squared plus k squared. And finally, that constant term, c, right? Well, here it's just equal to jk, right? So you said those equal to each other. So now, we know that we're trying to maximize AC, right? So given from these equations, right, how do we get AC? Well, you can just multiply this and this together, right? And if you do that, you get A times C is equal to JK times JK, which is, of course, JK squared. So now, essentially, of course, we're maximizing AC, which means we're actually maximizing JK squared, right? So now, how do you actually maximize? Well, first of all, jk squared you can rewrite as j squared times k squared, right? And the reason I am distributing and I'm simplifying it this way is because I see a j squared and a k squared somewhere else in my equations, right? That I found earlier. So it's probably a good idea to just to get everything the same, right? So let's rewrite this green thing here, right? So we have again j squared plus k squared equals 130, right? And we're trying to maximize j squared k squared. So I'm just going to write max. Well, now what? How do we maximize j squared plus j squared and k squared? Well, if you look at these two equations, right, you'll see that they both have a j squared and they both have a k squared. So right away, what I would do is just substitute like a letter in for both of them, right? So here, that what I mean by that is, let's say a equals j squared, b equals k squared, right? So that becomes a plus b equals 130, and here that becomes a times b, right? In my opinion, this is much easier to look at now. How are we going to maximize a times b, right? Well, we know that a plus b has to equal 130, right? So the only way to maximize an equation, right, with two variables, right, if you have like this a plus b structure, is if you divide that right side by two, right? So if a is 65 and b is 65, that's the only way to maximize. That's just, again, that's a really important thing to know, right? We're trying to maximize a times b, right? Um, the best way to do it is just to split the 130 in half, right? So now that we have found that a equals 65 and b equals 65, right? Let's get back to the problem. We know 65 is equal to a, and we said earlier that's equal to j squared. And we said b is also equal to 65, which is again equal to k squared, right? And of course, we're trying to find um, j squared k squared, right? Because that's equal to ac. So you multiply these two together. Well, that's just going to be 65 times 65, which is, of course, 65 squared. And what does that equal? Um, I would use a calculator for this, right? I wouldn't do it manually, but if you want to do it manually, right? There's a 5 there, that's a 2, that's 325. That becomes 2 in here. So I think here we're left with 0, 3, 6 times 6, 36. You add 3 there, you get 5, 2, 12, 4, 2, 2, 5. So again, that's just me doing the math, but I would use a calculator for this. We get 4225, which is going to be our answer choice here. C. So once again, right, for these types of problems, these constant problems, first look at what the question is trying to ask, right? So you know the end goal here is to find the greatest value of AC. Then they give us two equations, right, which have to equal each other, right, because one of them is just rewritten in a different form. Usually 99% of the time on these SAT questions with constants, right, you can match coefficients together and it will like definitely like lead you to the right answer, right? So once you match those coefficients together, well, again, go back to that AC part. You know, you're trying to maximize AC, find what AC is in terms of J and K, and of course, go on from there. So again, if you have any questions down, leave it down in the comments. Um, but I'll see you next time.